Hello, today we're going to be looking at derivatives of trigonometric functions, our sines and our cosines. So if we have y is equal to sine x, on page 25 we get the derivative dy dx would be cos of x. And if we start out with y is equal to cos of x, then dy dx will be minus sine x. And again, these relationships are on page 25. Anytime we do differentiation, we open page 25 in our log tables. Now, what we are going to do is immediately put this rule into practice. So we have f of x is equal to 4 cos x. Now 4 is just a number, so if we were thinking back to our earlier work in differentiation, this would just be like having 4x. This is just a constant multiplied by our variable. We don't need to use the product rule or anything complicated like that. This is just 4 times our function. So we can just use our rule without any complication. So we have, if f of x is equal to 4 cos x, then f dash x, or dy dx, is going to still be 4 multiplied by, what does our cos x become? Cos x becomes minus sine x. And that ends up being equal to minus 4 sine of x. That is as straightforward as we're going to get. So that's our just applying our rule without having to do anything more complicated. Now if we are given something a little bit more involved, like y is equal to 2x sine of x, what do I recognize that I've got? I have something multiplied by something else. I have a variable multiplied by a variable thing. So I have this 2x is something involving a variable, so I have to get its derivative multiplied by something else that I can get the derivative of. So I recognize I've got my product rule. And I set up my u and my v, and I'm going to use my product rule. So I set up my u and my v, and I know that from page 25 in my log tables, dy dx is equal to u dv dx plus v du dx. And I always write that pattern down. Don't try and take it out of the log tables directly when you're doing your substitution. Write it down on the page. So let's write down our u explicitly and our v. So I have my u and my v. I know I need to get dv dx and du dx because I've written down my formula. So dv dx, I go to my rule, and it just becomes cos x. There's nothing more complicated going on here. And I have du dx is 2x. That's just the power rule that I've been using now for a while. Multiply it by the power and subtract 1 away from the power. So this is x to the power of 0. So I'd just be left with 2 by 1, which is 2. So now I have all of my components and I sub in. I get u dv dx plus v du dx 2x cos of x. Always write anything that you're multiplying a trig function by in front of the trig function. So we don't write anything back here because it's very easy under exam pressure to get confused and think that it's inside the function. So 2 sine x, again the 2 in front, not left behind here, because we might get confused and think it was inside our brackets. And that's as far as we need to go there. So again, as always, this is a function that would give us the slope of the tangent to the curve of this function at different values of x. Now let's put this into practice in something a little bit more full on. So we have lots of stuff going on here. What do I recognize that I've got? Well, first of all, I want to rewrite this as clearly as possible in power notation. So I'm going to use brackets for that. I recognize that the cubed here means that the whole of the cos function is cubed. So not the stuff in the bracket, but the whole cosine function is cubed. So now I've written this in power notation. I see that I have a function cubed. So something cubed is a type of function. Cos is a function. And I have stuff inside the cos. The x squared plus 1 is another function. So I have a function inside of a function inside of a function. So I have composite functions, nested functions. That means I'm going to use the chain rule. So let's put the chain rule into practice. Here we are going to do our chain rule by differentiating from the outside in. Because if we did it by substitution, we'd have to do a substitution inside of a substitution. It would start to get very, very complicated. So we want to differentiate from the outside in. So treat the bracket like it was an x. So now we're dealing with dy dx. Treat the bracket like it was just x cubed. So the bracket, multiply by the power. Just rewrite the bracket. Subtract 1 from the power. That's the outside differentiated. Then we step inside, and our next thing is the cosine function. If we differentiate the cosine function, we get minus sine. So minus sine of x squared plus 1. Close our bracket. Then we step inside for a third time, and we have to differentiate x squared plus 1, and we're going to chain that along. We're going to multiply that along here. When we differentiate x squared plus 1, we're just left with multiply by the power and subtract 1 from the power, and derivative of a constant is 0, so we're left with multiplied by 2x. So we differentiated the bracket, differentiated the far outside, then differentiated the cosine, and then differentiated what was inside the cosine. And that's how our chain rule chains our derivatives together, multiplies them together. And then we have to be careful. What have we got multiplied together here? We have our cosine is still squared there. We have a minus, a 2x, and a 3. So we're going to end up with minus 6x as our non-trig stuff outside here. And we're going to write that first. Then we have our cosine is squared, and x plus 1. And then we have our multiplied by sine of x squared plus 1. And that is our dy dx, nice and simple down, simplified down. Now, this has ended up as obviously a very complicated function. So what we're going to do is link this back in, as we always try to. And what does this mean? It's a function that gives us the slope of the tangent to the curve of this function. It gives us the slope of this function at different values of x. Even though it looks heinously complicated, that's what it does. So let's find out what dy dx, what the slope of this curve, or the slope of the tangent to this curve is at x is equal to 3. When I sub in x is 3 into all of this mess here, 6 on 3 cos squared of 3 squared plus 1 sine of 3 squared plus 1, all of that works out to 6.89-ish. So rounding to 2 decimal places. Next decimal would be 4, but that'll be accurate enough. This gives us the slope of the tangent line to this curve at x is equal to 3. Now let's show that and see that it does in fact work out. This function looks very weird, so just prepare yourself for it. The screen is about to get brighter. So this is my function that I was dealing with. G of x, as I've written it here, is cos cubed of x squared plus 1. And this is what the function looks like. And I have picked the point x is 3. That's my point on my curve that I've decided I'm interested in this time. And I have my tangent line equation here, and I can see that my slope of my tangent to my curve, this is in the form y equals mx plus c. So the slope of the tangent to the curve is 6.89, which is what we got when we subbed into that function. So again, this function that we're finding gives us the slope of our tangent line to the curve at different values of x. So we sub in a value of x and we get the slope of this black line as we're going around. And obviously, if we move around our point, this function that we found would give different values for our slope. So the slope of this black line as we're moving it around is what we would be getting. So if we had x is 0, if I'm able to stop it at that point, it's being a little bit awkward with me. If I was able to stop that exactly, right, I will stop it here. Now, if I get my line, if I get my point A to stop at x is equal to 0, I can see that my slope is 0. So this would be a turning point of my function. This function has many, many turning points, but this would be one of the maximum points of my function because dy dx is being 0 at this point. And again, the function, if I go back to my original, my function here, dy dx, gives me the values of all of those slopes of that black line as I'm moving around my different values of x. This function would give me the slope of that line as I'm moving my value of x. So that's what I need for my derivatives of trigonometric functions.